Good. So let's welcome Dr. Chien Wang.
Thank you, and thanks for getting me here again. So, it's wonderful after Phil gave a talk after Phil. So I took out those introduction pages. So anyhow, to just show my series to this workshop, I'm going to talk something I haven't been done in a long time. These are my homework. So I have a lot of the result you're seeing probably it's not came from my postdoc or student for a long time, quite many of them. But I'm going to talk switch a little bit gear toward the climate response of aerosol. So much of the attention actually in the past, maybe a half century already, about aerosols remained on the forcing side. It came from quite a few reasons. One is, ever since Subion Manabe's time, he believed climate model as the response to all these forcing agents probably within a statistical significance. So which means it doesn't matter what you threw into the system as far as the definition of the forcing keep consistent. You're going to receive the same response accordingly to the forcing strength. This has been holding very long until black carbon and the indirect forcing come to the house. People start realize that this long-standing linear scaling factor has been threatened. So there's a concept being thrown out from efficacy from Jim Hansen and the effective forcing from a recent IPCC report, which I have to say that's quite a strange idea. And this is only based on two peer-reviewed publications, but you will see that it has very strong reason. I will show that. So anyhow, let's try to remedy this. And also based on these fundamental beliefs that as far as they tell me the forcing, I will tell you the response to the aerosol. That's where, partially Bjorn and the others, the comment came from. I'm going to try to tell you this is really dangerous doing this because equally or even more, poorly understanding about the response might really is something we need to address. It's fortunately in recent years, more papers, more models has been formulated to have a capability for us to address the things. And the very first thing is, I don't know anyone in the room can tell me in the straight face we know aerosol evolution in the past, which actually is very, very amazing understanding in this field, because we bet so much on the satellite, and it turned out even the cellular retrieval people tell us don't do anything about the trend. So we therefore recently tried to search alternative way to understand what's going on in the anthropogenic aerosol. So we're looking for over 5,000 stations over the globe, which is reporting visibility. We know that's just a surface AOD, aerosol optical depth. So what you see here is over almost 4 decades, we chunked into different, each individual decade, so you can see that. And all these things actually fit into our, what we learn from a news report, but never been reported scientifically, actually. You can see all these places you expect, except probably people would wonder why China is less hazy than India. But I think we have pretty much confidence on that data. So, it has been, general message is, the particulate matter has become worsened, the pollution. And if you look at the trend, the same, again, linear trend. So you can see clearly in the North America and the West Europe, you can see the blue trends ever since, Clean Air Act in the US, and also the widely pollution control strategy in West Europe. But in the other part of the world, and in particular getting close to nowadays, you can see the red spot, the old around all these places. Recall these, the dark red in the previous figures represent about a half of the time in a year you're having haze or the particular matter. I had a really funny photo showing what that really means, but I took that out to save some time for science. Okay, so same as the Phil's group did a lot of wonderful work, and parallelly, my group at MIT also built a model. This model, probably a lot of people in the room already know. That's the only thing new is that we finally get a name for the model. They told me without a name, nobody knows what you did. Anyhow, so we have all these carefully treated, but however, really carefully also weight computationally. The aerosol process. We have 7 different types, maybe getting more. And there's a mixing mode here being specifically unique compared to other model. We treat black carbon and sulfate mixture with a core shell structure, and all the physical and chemical process based on that, and also had a mix. So you couple with anything model as far as it provide meteorology and also connect to the radiation and the cloud. This model will be there. So we already put it into the CESM, now it's a DOE and CESM, and we're working with the GFDL team now. We help them to see if that model can work over there as well. Okay, so once you put these aerosol into here, I think this would be more or less you would see where the forcing locate. First of all, we know there's a very heterogeneous dispute. On the top is a direct or the aerosol directly interact with solar radiation. So you can see all these hot spot place, and these are specifically important. This is black carbon and other absorbing aerosols. So you had a red absorbing in the air. And here is a lot of cooling place if you look at the TOA. And if you add, again, the aerosol-cloud interactions are formally called indirect effect. So you will see even a larger effect over the northern hemisphere. So general hemispherical-wise, you have a cooling over the north, and there's damping effect. On the south, a little bit of, these are maybe noise. Okay, so one thing you can do is, treat it as same as the other agent, forcing agent. Just see, equilibrium run, which means you have, nowadays we use AOGCM, it's coupled ocean. So put it there. Let this model just open evolving. We had a 200 years. It's not long enough, but you can see the transient feature already disappeared a lot. You can see this not actually reached the real equilibrium, but pretty much up there. So we put with all other conditions same, you can put 1850 pre-industrial aerosol, and nowadays we had many other fancy runs. Here's the 2 things that we only include the indirect effect. So let the direct effect out. What you can do is, you can estimate what is the long-lasting effect of aerosol. That's the first step, in my opinion, to understand how the Earth system respond to these forcing. You can see here, I purposely make them a really dark green, so you can see generally it's cooling over everywhere. It's after we use last 60 years of this 200 years run. So you can see here cooling everywhere, and mostly not just located in these aerosol hot spot, but also widespreading. Well, I mean, these are just surface stories. So, well, people measure. We in the past actually, Manabe's time actually the climate sensitivity is mentioning actually based on the equilibrium concept. You can write the energy budget in this format and here, although all these are time dependent, but when you have a constant forcing and a constant climate sensitivity, or this actually feedback factor is 1 over this, then you can make assumptions, say, your forcing in general will create a residual in the top atmosphere energy budget. So if to see if a system evolve enough, they will merge into either delta H disappear. Let me tell you, that's impossible. Okay, so or you can form a linear regression, as Richard Andrews and Foster and others tell you can do, and linearize the whole thing. Here, what I see is what I put is the DH on the vertical and the DT is horizontal. So we have 4 runs. You don't really use one individual run because that's greenhouse gas are also inside. This type of thing is actually a pulse. You launch an incident pulse into the model, let them evolve. So you compare 2 runs and try to calculate the delta H and the delta T. You see here is interception will be the forcing if indeed the model is going linearly, and also the slope will tell you the sensitivity. So it's very interesting. You see this formal order still kept. You can see there's a almost perfectly parallel line, which means that the system will respond the same. And it's rather disappointing, right? So that's my original self must be wrong. Anyhow, but this is just, and I can tell you the value, it's very close to a CO2. It's about a 4K, or in the double CO2 forcing. Well, if you look at all these data carefully, so you can actually derive the forcing, how much forcing is. So that's where the really interesting things come from. We have been very carefully follow all the common procedure to calculate offline exactly how much forcing we have. Okay, so this is what we calculated here in the bottom, and what you can linearly regret. This forcing is far before reach this level, so which means the model only failed a scale of forcing. That's where I say all these people argue about effective forcing really had a point. However, this is a very dangerous thing because you see this arbitrary scaling. There's no way to make me convinced about the physical background of this. Universally, each model will have physical background. And also the equilibrium temperature, you can actually calculate once you regression done, you can calculate the equilibrium temperature. You can see here is also difference. So if you assume your model reach equilibrium and use this known forcing, you can only reach about slightly more than half of the ECS. So this is the whole thing. The firstly in the equilibrium, or you can say the aerosol in an equilibrium condition, aerosol is less effective. That is, this might be wrong, but okay. So let's settle the equilibrium things for first. And what about the transient? Because transient is most people argue that's better way to measure how climate system responds, because we never expect the climate system in a really equilibrium state. So you have to looking for some others, no one can afford doing that many runs. So you looking for the simplified model. Among all these models, 16 of them claim they include indirect effect. So this is what I am looking for. And 4 of them had various issues. So finally, I have to pick up 11 model among these. So all these models have 3 required runs. So one's, this one, the brown one's historical, start from a pre-industrial all the way integrate to current. This include all these forcing people know, we know of so far. And there's a natural run, which is excluded these, but includes natural forcing. And this will only include greenhouse gas, so that's a lot of warming. So the message is quite clear. Without other balance, this blue here is no one actually run this run. So this just you assume the linear. That's very dangerous again. So you can derive this and the blue. So otherwise, we will reach somewhere about 1.5 degree warming, and just because most our aerosols we shed out these warming, so we got barely 1 degree. Okay, the concept is quite straightforward. So how to estimate transient response out from there? Recall none of these model reporting actual forcing. I don't have confidence they know it clearly what forcing they have actually. Again, there's a few ways you can do that. And certainly, you have to use these, all these forcing minus greenhouse minus nature to derive these non-greenhouse gas effect. Among these effects, there's a land use land change and a direct effect, indirect. So the first method you can do is assume, okay, the aerosol and the greenhouse gas had the same climate sensitivity. Remember, all these are time independent. So if you assume them, so you can use them because these two are model output. So you can use this to inversely derive the forcing along the time. Then you can estimate, delta T over delta F to give, time dependent estimation of the transient response. Although the real transient response is defined by certain things, but anyhow. So this is one thing. Obviously, this is a really heavy assumption over there, and it's against my interest. A second way you can do is you assume the temperature effect was caused by tropical ozone in land use pretty much balanced with the aerosol direct effect. It's pretty much true if you look at the forcing value. Then the rest will be only indirect effect. Now you can use a called shortwave forcing, which you can also derive from a model to simulate that effect and use that as a proxy to estimate the transient climate sensitivity. And certainly the last one, it's I tried. It's not a good idea, so I'm not going to talk about it. Okay, so after all, again, you see this linearized world, so beautiful, but so disappointing. Okay, so the horizontal, you can put a forcing at a horizontal and the delta T. At a vertical, so this generates tell you the slope, tell you the transient response. So the red is the one, if you use the cloud forcing, shortwave forcing to simulate the whole thing. And the blue is you assume the aerosol and the greenhouse gas have the same climate sensitivity, so you inversely derive the forcing. And you can see here's a linearly toward the low side. So actually, it should be more reasonable. Should be toward this. So the slope should be a lot bigger than that. And first of all, this actually had a purpose. I put it here. It came from the belief of the response has a saturation. Very, very disappointing. You don't see any saturation, the sign, okay, here. So from my early work on the convective response, we do see the response saturation, and also stratiform cloud also too. So which says whatever they did to formulate aerosol into the current climate model, at least you don't see this saturation yet. So which means it's still cloud the system respond really, really drastically. And if you look at, I did the time analysis as well. These things become even significant in the recent 3 or 4 decades. Well, Chien, though, colleague of mine, organized a chemistry model in a comparison before, parallel to the CMIP 5. So they have 5 model reporting forcing, and he did some estimation. It's about aerosol's transient climate response. It's about 1.5 times greenhouse gas, which means aerosol is more sensitive to the climate change. In particular, the things become more dramatic during the recent few decades. And here, my number is slightly close to about 1.3. So if you calculate, Well, certainly this will be 1.1. That 1.0. I mean, it's the old order line. So we think it's not really the correct result. Okay, so the message now become a little bit bizarre. In a transient climate, the aerosols are more effective. And this thing has become really interesting because the aerosol forcing getting bigger according to all these climate models reached the recent decade. And if you really consider let the model cook enough, and aerosol might not be, that's different interpretation. You might say aerosol might not be effective as a greenhouse gas or due to other reason. Anyhow, so my brother Chien had some alternative explanation. He said, he did use a 5 model again. Your opinion. So he did hemispherical partitioning. So he found actual aerosols more sensitive because that's a reason has been the heterogeneous partition over a hemispheric scale. So you can see all these things perfectly line up at 1.5. That's the reason. Well, why, it's to tell you the original beyond the Steven's comment is actually my concern about the saturation is looking into the future. And all these greenhouse gas forecasts from, whatever, people did to the energy assumption, they all goes up along the time, but except aerosol precursor in the primary. So if we do have a nonlinear response, and when people learn, know the thermodynamics lesson, that's Carnot cycle, and when you shut down from upper level going back, which path you assume the system would follow. So these are the fundamental worry or the concern I have. Why I'm so interested about this. Okay, so the temperature is the most boring part, in my opinion, related to the aerosol, because the aerosol is such heterogeneous distributed species. Precipitation might be better. So, well, if we line up the equilibrium and transit, here's another shocker. So, on the top is our equilibrium run. You have a standard 2000 aerosol and minus a pre-industrial aerosol comparison the last 60 years on average. And here's all these 11 simplified model. This is an ensemble average. You can see the striking similarity on all these precipitation distributions. So which means the aerosol actually dominate the precipitation distribution. This is, keep in mind, this is having the greenhouse gas forcing inside. Okay, so looking into the slightly detailed, the more detailed zonal mean feature, you can see even clearly here. Here's again our equilibrium run. So this is annual on the dark black, and the other two is a different season. So you can put all these all these runs a historical run. They call historical. So you can see this very, very clear southward shift. We know the dynamically roughly well now. Why? It's just even with greenhouse gas, the similarity is so striking. And if you can see with all these derived non-GHG or actual aerosol, these two that's also very similar. And in opposite, the run only include greenhouse gas, it will give you totally different distribution. Okay, I think there's a pretty strong case on that. So although when you're talking about the temperature, generally you don't have to worry too much about aerosol in that sense, although the distribution might be a factor. But for precipitation, this is something. Mark Saltzman recently also did some interesting analysis. I thought about doing this Indian monsoon thing, but Mark did it one step earlier. But I just express his result in my understanding. So forget about left. What they did is the same. They use a historical as all forcing, and a natural and the greenhouse gas only. So you can see if you're doing these precipitation trend over this region now, bringing a lot of interest now. you can see the trend is totally different when you have aerosol, compared to the greenhouse gas only. The sign will be opposite. So the precipitation pattern will be really heavily influenced by the aerosol. And if you look into their magic number, I hate magic number, by the way, they just lump up the total precipitation over that domain. But it's a very clear message. If you have all minus GHG, that's the way they interpret the aerosol. So you will have, in the past half century, very clear, significant reduction, negative trend. Market managers find that 3 or 4 models actually run the historical only include aerosol run magically. So this is very consistent, which means, again, my assumption made is not too bad. You assume all these things are due to the indirect effect, actually. Here's a 2 observation, CRU, people probably know, British database, and UDEL. So these are both showing very, very supporting evidence to the model result. And the land use changes, it's a different story. So, okay, let me wrap up. I think the message is somewhat clear, I hope. The first thing is we found really the transient climate response to the aerosol is larger than greenhouse gas. So now it's at least 2 independent estimation. Well, I didn't mention the equilibrium of things. We're still absorbing that result. I was interpreting that as the equilibrium response to aerosol lower than the greenhouse gas, and I realized you need to interpret it differently. Now my thought goes to aerosol-cloud radiation effect. That's it's a delta H. You just see there. I'm doing very in-depth analysis actually in the flight over to here. I'm still running out. That's why I bring this big laptop with me. Anyhow, that's the only time you can have good time to run your things. So that will be, I hope that can tell us some story. It's pretty clear now. Well, it's the same as Phil mentioned. Now the Meso-Globe model, or we know the well-documented model, including ours, actually giving a lot higher indirect forcing compared to direct because of balance of black carbon. It really brings worry to me, actually, because we lack the skill compared to include the direct forcing in the model. So this really brings the open, it's a good thing, open the whole door for a lot of young people in the room to work. It's a really, really interesting topic. And talking about precipitation, at least from my perspective, my reading of all these results is anthropogenic aerosol actually played a very dominant role in determining the precipitation change pattern. You might argue about thermodynamics is part of a total precipitation change, but who cares about total precipitation change anyway? So, okay, I will warn you the last is all these impacts you see on the precipitation actually reflect only the dynamic effect. No matter you call that direct forcing or indirect forcing. I wrote recently a review paper, and I put that in the term, I said, dynamical path. Many people had confused. This is what I really mean is the effect is rather through the it's instead of through the microphysical process, actually through the the dynamical effect. It's forced through the radiation and the dynamical circulation, alteration, and come to the precipitation. So all these effects you see, it's not really come from microphysics, or you change the stability of the whole hydrometeor family and reduce the precipitation. It's not really, actually. These are really, really arbitrarily tuned in the model. Anyhow, so I guess I told you the clear story now. I'd like to entertain a question. Thank you. Yeah.
So Professor Wang already raised his hand, please.
I'm curious about your last point. What is a radiative dynamic you define there? You mean that includes cloud macro properties like cloud cover, or vertical extent, rather than the microphysics?
Yeah, the macros, what I really mean is you really affect through physical effect and in fact the formation of precipitation. We don't have such skill in the climate model. Even people claim not to be, and you don't believe that. So these effects will be caused if you cause, if you cause cloud change, for example, and you reduce the overall micro radiation budget, and you put a alteration to the circulation, you change the whole circulation, or you shift to the, these are the ITCC shift is generally overturning circulation because hemispherical cooling.
But
these are caused by aerosol.
But the microphysics can feed back to this large-scale circulation.
Yeah, that's only in theory. Yeah.
Only in theory?
Yeah, because in the climate model, you don't have such, these are so-called tuned by the auto-conversion, right? So these are really, I don't really want to go into detail.
But yeah. I might argue that on a regional scale, for example, black carbon can create a very large heating in the regional
that's the dynamical. Yeah, this is a dynamic.
But then that can create a dynamic response.
Yeah, this is what I meant. This all these things you see is majorly forced by such process.
Okay, so that's
in the climate. Yeah,
not just.
I call it dynamical path because in the past, classically, people say as microphysical effect. If you increase so many small particles, you decreasing the aggregation and you form a ring slowly. You don't really doing that. But I have really low confidence about the current model's skill. I don't see that.
Well, maybe Phil can.
Yeah.
Well, I'm interested in this too, but I would have characterized it differently because to me, I think maybe the models overestimate the importance of the microphysics. So, and I mean, it manifests through a change in the radiative dynamics, but it's not like the microphysics doesn't matter in the models. It does matter a lot, right? It's just, it might not be very good.
I don't know. That's why I'm saying I don't know. And most model actually does not have that educated auto conversion scheme.
You're talking about in the convection, or
no? Yeah, convection is the most.
Well, in the stratiform, I mean, of course. There are representations formally of those processes. Whether they're any good or not is another matter. But and they're extremely sensitive to the assumptions that you put into the model, right?
That's even bad because I mean,
I don't have much confidence in them, but I think they're really important. I mean, I think that they're really important in climate models. Yeah. Even if I don't, if I wish they were better.
Yeah, I think I would take a right on your comment on the convection. Actually, the most change you see is convective precipitation. Yeah, I doubt it. Yeah.
There's not much in the convection.
Yeah.
That's for sure.
Yes, we have a microphysicist to defend him.
Yeah, I'd like to follow on this question. I think Phil is right because if you use different macrophysical scheme in the model, you get very different results.
Yeah,
and that tells you the sensitivity of the microphysics.
But that's a large scale. Probably you see it in the Arctic. Yeah. In the tropical.
Large scale.
In the tropical, it's both.
Sure.
Yeah, mainly it's a convection.
Well, there are direct microphysical effects and indirect through the dynamic feedbacks.
These are important. These are if you're talking about the indirect, these are the radiation things. So the dynamic can form by indirect effect because you change the cloud reflection. So you had a forcing. Actually, there's a forcing sensed by dynamics rather than the microphysics process.
Yeah, we recently worked with the Chinese academies, and they did some tests on the microphysics scheme using our scheme. They found they have huge amount of ice clouds in the climate system, and also, yes, but it's not properly installed yet.
Yeah.
But just through such sensitivity, you can tell the microphysical scheme is very important.
But not for precipitation.
Yes, it is.
Oh,
yeah, also precipitation change.
I'm a little worried about that model. I'm serious. The precipitation is generally dynamics. You know,
Yes, so I actually agree
yeah.
with you because
Yeah.
precipitation also change with your microphysical scheme,
Yeah.
and that's not right.
Yeah, so that's why I want
It's
to
sensitive,
bring
yeah.
people's attention to here, my concerns. I mean, really, it's a good and bad. So it brings, you know, really, yeah, the load on the weak side of our skills. Yeah.
Any other questions? Okay.
Okay. I know what you're saying.
I'm sorry, a little bit late, but fortunately, not too late. I got to see the summary. Actually, my question is from observation point of view. Can you identify some really solid observations that shows the aerosols impact on precipitation?
Yeah, there are some. You know, the Elan-Coren's work Phil mentioned before, but these are not case by case. So the case is mostly stochastic sometimes. And likely you don't know whether aerosol interact with a given cloud, which, you know, aerosol has to come to the cloud base level and interact with the dynamics correctly. And also quite often if you follow one case, you might find there's an observation showing, you know, the precipitation change, or some model combined observation, the aerosol overload might change the phase a long time. So you might get a rainfall earlier or later, but total precipitation might not be that. So the current, you know, as far as I'm talking, interest is on the large scale dynamics. So there are some, mostly from satellite retrieval. So these are the global wise. Yeah.
Well, the satellite, the year 2000 science paper by Rosenfeld, which is very famous, famously wrong, you know.
Well, he cited many right work, including mine, but he just made a wrong explanation.
Yeah.
Maybe some. Yeah.
And his works following that pretty much.
Well, yeah, there's a.
Wrong.
Yeah, I really enjoy the precipitation discussion. So that's really bring all these scale we care about in the atmosphere. So you're talking about a really macro scale all the way to the dynamic feedback. We know something, you know, through detailed study, include the radar observation and the modeling, cloud resolving model study. We know the physics, and this is for almost a century, the climate macro physics. So the so-called integration, which is realized not too far, after recent, maybe 20 years, so include my early paper. So these are, you know, the overloading effect when you form a lot of ice in the upper air. So these are physics, it's understandable. But whether they can convert effectively into precipitation, that's the argument. I think Danny did really good job on summarize that lack of a knowledge part. So yeah.
So my speculation is, I mean, maybe the changes in precipitation is through changes in precipitation patterns, as you've talked about, but also by changing the dynamics of the cloud, you can change the ratio, for example, of precipitation in the convective updraft to that occurs in the stratiform anvils, and that can actually have really important impacts on the vertical profiles of the heating rates as well, which is important to the large scale as well as because it changes the altitude at which the heat is released in the atmosphere. So it's important for a variety of reasons, right? Even if the net flux of precipitation reaching the surface isn't changed so much, where it happens and at what altitude the heat is released can make differences.
Yeah, I agree.
I think.
Totally agree. Yeah, totally agree. But You know, from what I understand, you know, Guangjia and others doing this convective parameterization introduce aerosols. It's basically down to the updraft. That might be another issue. Yeah, I agree. There's a feeder-seeder things in the classic microphysics. So if you got the convection and stratiform partition right or parameterized in this sense into a climate model, that might be a key. At least change the heating rate. And I believe that would be very effective to the precipitation as well. Because in the tropical, people found well cooked the stratiform portion actually is very important for long-lasting rain. So this could be, it might take time. They work only in the updraft, so that doesn't even include the so-called cold pool feedback to the cloud dynamics yet. So.
Okay. So we have to keep our schedule, so maybe we can move some of the discussions offline to the break time. So let's thank Dr. Wang again.